thank you everyone for staying for my talk. I'm gonna try to address the question of, is there an optimal wavelength for GUV? This is inspired from coming to this conference last year and having many discussions about all the light sources that may be possible and all the phenomena that depend on wavelength. I'm thinking that maybe going to larger wavelengths, maybe there will be a solution. I'd like to start by acknowledging my colleagues, Jeff Tang and Joe Segal, working on the pollution side, and Belma, who's a former student of Linden, who has advised us on the disinfection rates to use, which is a critical part of this work. So yeah, so again, we all want to maximize disinfection and safety, and the first one to appreciate how good we need to have a airborne disease control technique that was acceptable. And we know, but then we have a bunch of different things that they are wavelength dependent. The skin and eye we've heard about, also the disinfection depends on wavelength, and there is some inconsistency there between the studies. And the pollution depends on wavelength, but almost all the studies have been done in 222. There is one I know in 254 and not much for other wavelengths, even though we do have the knowledge to understand what happens there. So anyway, so what I'm looking for the holy grail. Is there a holy grail wavelength? Being in the UK, I thought the cartoon from Monty Python would be appropriate. And so we're going to do model runs when we're going to assume that we can have a 1 nanometer wide monochromatic source. We're going to run a constant disinfection. So if we have a disinfection constant, we will turn the light so that we have 5 equivalent changes per hour. This is in a typical classroom. And we're going to be assuming that we're working with SARS-CoV-2 and surrogates. And we're going to try to calculate a single indicator of pollution and see, when we keep the disinfection constant, how does this indicator of pollution vary with wavelength? And we are after the relative trend, not the absolute trend. So is this pollution a concern or not? That's a question for a different talk. It's like, is this wavelength better or worse than this other wavelength? That's the question I'm trying to answer. Okay, so starting with some of the background, most people already know this. So this is the RNA absorption that people have already presented here. This is the protein absorption that increases and then starts to turn down at 200. And this is the skin cancer risk increasing after 280. For reasons related to the limits that have been discussed here, around 235 or something like that is when we can start to do whole room applications. And above the wavelength, we start with the upper room application. Now, the most important slide of the talk maybe is this disinfection efficiency versus wavelength. And here, Ben Marr really helped us to try to synthesize, what's there in the literature and how to make sense of it. So this is the study that Ben himself presented from his PhD with Carl Linden. And we see, some values here that are relatively constant in this longer wavelength and higher disinfection efficiency at 222. Now, there was a study by Schmidt that was published that doesn't quite see that trend, sees a decreasing trend when we go to 220. And importantly, we have to multiply this study by 4 by scaling them at 270 in order to get to understand the relative wavelength dependence, which is where we're at. Then there was a study by Fujimoto, which are those data points that again has a decreasing trend with wavelength, and Fujimoto published a fit. What they propose is the disinfection efficiency versus wavelength, and we're going to do that as one of our cases. And this one we have to multiply by 2.4. Then there is the study that we saw yesterday from the group in Hong Kong, where they see again, in this case, an increasing efficiency of disinfection at 222. And we saw also the study from Felix Essinger. That was another study yesterday, but in which they also don't see this increase, they see this decrease. I don't claim to be an expert on that at all, but we are going to just run 2 cases. So we're going to run one case that is this Fujimoto case, and another case that's the same in the central region, but we call it the hybrid case. So here we're going to shoot up with the protein absorption relative tendency and going through Ben's point, and then keep going up, even though this may be unrealistic, just to get an upper limit of what the disinfection would be. And on the right side, we're going to go through the higher disinfection coefficients rather than the low ones. So this is what we're going to be running in these 2 cases. Just as a comment, from compiling this data, there is a factor of 20. If you look at the scaling numbers, there is a factor of 20 absolute difference between the studies. Each study, once you scale them, they're only a factor of 2 to 3 different. We're looking at much smaller difference. So there is really something systematic with the studies that gives us much different disinfection efficiencies. And actually, this is the biggest challenge this field has, is, where are we? What's the real world? If it's really, we're really at the upper limit and disinfection is very efficient, frankly, the pollution gets pretty boring because it's very small. If we're at the low limit and we need to increase the fluence rates, then unfortunately the pollution gets interesting. So I would argue if I had a non-profit that was funding studies, this would be the first thing I would fund. Okay, so now air pollution versus wavelength. So it's due to molecules absorbing light. This is ozone that starts absorbing at 245. It's multiplied by number, but it has a very strong dependence in this long scale. Now we have OH formed by ozone photolysis. So we break up ozone, and this maximizes the different wavelengths. To answer the question from the gentleman earlier, it doesn't work to use 254 to break up the ozone because 90% of the ozone forms right back, and the other 10% makes two OHs, which are much worse than the ozone. So that's a bad idea, I think. There are other ways to reduce the ozone that are much better. And then this is we can also break up water at low wavelengths to make OH, and that's pretty bad. And there are other functions, and there are more that I can show you here. There's a whole bunch of wavelength-dependent things, and this is not obvious to me as a chemist looking at this and seeing how let's predict how the pollution is going to look like. And basically that's the chemistry. We have the primary chemistry, and then we have what we call the secondary chemistry. These ozone or the OH radical are going to react with other things, with VOCs. We've heard, for example, from Charlie, there is a paper that someone used sent me yesterday, in which people see that with SO2, which will be important in places like China, actually 222 also makes a lot of particles, and we're going to study that ourselves. It's important to realize that this is going to depend on how much of these VOCs, for example, we have. And we know from studies indoors from decades that there is a factor of 100 difference between different indoor locations. So if you go to an indoor location where the VOCs are low, you're not going to see any PM formation. And if you go to one with is higher, you're going to see PM formation. And the next two talks are going to be examples of exactly this. One sees it, one doesn't, and I think we understand the reasons. So in terms of we're going to build a model. I'm not going to give you details. It's also not too much for this audience, but I just want to convince you that the model is trustworthy. We're building on the model is the repository of the knowledge of the community, including giants like Charlie Weckler. And we have been working for a decade on using UVC to make pollution. This is something that we do in atmospheric chemistry, and actually that reactor is the same that Felix Essinger has adopted for his studies. And Johan and I have written a review on that. And also we showed last year that we think we understand how ozone works. And we published a paper this year. We think we understand how organic aerosol works. And this is from Lemon. This is a study in the chamber, but we've also done the study in the office. And there is a little aerosol formation because you lose more to the walls, just like ozone, but the model still captures that. Finally, we want to come up with a single number for pollution, and the most important impact is mortality. So we're going to try to see how we can combine that. So for example, this is the epidemiological function for PM2.5. And we say, okay, if we increase PM2.5 by a microgram per cubic meter at the levels that are typically indoors in the US, this is for the average in this case, then you will increase all-cause mortality by 1.3%. And for ozone, we use the study that Charlie mentioned, and he had lower numbers. So then when you combine the two, we define a mortality index, which is how much we increase PM2.5 plus how much we increase ozone in micrograms per cubic meter divided by 26, meaning ozone per microgram is 26 times less potent than PM2.5 at causing mortality. And we can argue, is this 26, is this 23, is this 30, but this is not 1 and this is not 1,000. Okay, so it's a number that I think will be useful for that. Okay. So this is the key result, looking for the Holy Grail. This is the pollution, this pollution index, when we keep disinfection constant. And we have two curves because if we have less efficient disinfection, as in Fujimoto, we need more light, and therefore we make more pollution. If we have more efficient disinfection, in this high wind case, we need less light, and then we have less pollution. So we're normalizing by disinfection. Okay. And you see a bunch of steps here that I try to explain. So if you go below 200, it's really that you make a lot of OH from water, and things get a factor of 10 to 100 worse very quickly, and then you start to make more ozone. So really, as a community, these lamps that make 185 are really dangerous, and that's something that needs to be eliminated and can give a bad rap to the field. Now, it's unfortunate, and this is not what I was hoping, but the moment you start making ozone at 245, the pollution starts to increase. The disinfection is not increasing fast enough with wavelength here, or not increasing at all. So really, the moment we start to make ozone, we have a step. And then exactly the plateau depends on which function you're in. Now, if you go below 300 here, the pollution is very high, at least with the Fujimoto case, and that's because the disinfection rate constant is so low that you need a lot of light, and that generates a lot of pollution. I should say, see people taking pictures. This is not published, so please don't post the pictures in any public forum. Right in the paper. So anyway, so then in terms of evaluating these results, I would say, definitely below 200 there is too much pollution. I think everybody knew that already. Above 280, we start to have the cancer risk. If we have an accidental exposure and maybe have low disinfection, it's very uncertain, so that doesn't seem like a good place to work either. This region in the middle, which last year I was naively thinking maybe was the holy grail, is not, because basically between 235 and 245, something like that, you're stuck in the upper room, and you have more pollution than with 254, so why would you do that? So then we're left with where we started. We basically have this whole room for UVC, and depending on where you are, 222, it's maybe better. Maybe you can do marginally better in the Fujimoto case, and it doesn't matter on the other case. Or you can do things in the upper room, where the pollution is, for this case, a factor of 20 lower. This is an average case. But that factor tends to be at about another magnitude. And again, 254 is there, and this is very small variation. Things are pretty flat. Okay. So let's see. So is there holy grail? No. Now this ratio between 222 and 254, since basically we have two flat regions, we can explore that ratio versus conditions. And that's shown here versus the ventilation rate in a log scale and the relative factor of indoor VOC emissions. And so we're working here at 1.1, we have a factor of 20. And you see that, it's always kind of like another magnitude, in some cases maybe a little more, but it's about another magnitude. So it seems to be robust for the conditions. And so in conclusion, going back to the simplified version, we're left with where we started. We can go to the upper room, and we have these issues with installation and accidents and whatever, but we have lesser pollution. Or we can go to far UVC, and we like it that it's on the whole room, but we have more pollution. So we either need to limit the fluence rate, and that depends also how efficient the disinfection is, or we have to do some pollution controls. And we've been testing, can you show the results, but we've been testing some awesome catalysts in our lab that I'm told they're very reliable, and they seem to work very well. So I think and they're actually not very expensive. So there may be ways to mitigate the pollution that are very useful. Thank you.